Hi there! On the bench today, a clamp meter for measuring leakage currents sent in by Banggood. I did not pay for it, so I mark it as promotion, but as you know, that doesn't stop me from giving you an unbiased review. In the box we have a manual which is surprisingly entirely in English. Do they substitute the manual for one in a different language if it's sold to other countries, or simply assume everyone is okay with English? I assume it's the latter. Next, we have a carrying pouch which contains the clamp meter, the usual bag with leads and thermocouple, and a USB charging lead. The meter is quite small, which makes the clamp look comparatively large. The model is apparently the WinAPEX 268C. Turning it on, and after a quick display test, it just shows lines of dashes. I suppose it's in auto mode. Indeed, pressing the red button again, and now it's in DC-volts mode. First impressions, I do like the display. It's very large and bright, easy to read. On the rear we have two sockets for the leads. The right side sports a USB charging socket covered by a bung and another button, and that's pretty much it. The leads are so-so, rather stiff plastic, but rated for 1000 volts, and the probes for 1000 volts Cat 3. Refreshingly, there is no dishonest cat rating printed on the meter. The meter narrows at the end, so the two sockets are much closer than the standard width of 19 mm, rolling out using BNC adapters or dual banana plugs. This narrow spacing is even a problem with the leads that came with it. They should have used straight-ended plugs, not right-angled ones. They interfere with each other unless you let both point down, which means the meter doesn't lay flat anymore, or you let them both point up, which makes reaching the lower buttons difficult. You best use them one up, one sideways, as ugly as that looks. Actually, strike that. The best solution is to replace them with straight-ended leads anyway, but in this video I'm using the probes that came with the meter. Let's go briefly over the buttons. You turn the meter on or off by a long press on the red button. The display briefly shows all elements. Let me freeze the video here for a moment to show that the display legends are actually mirrored to allow the display to be flipped. After the display test, it shows 4 dashes indicating auto mode. A brief press on the red button gets you into manual mode starting with DC volts. A long press on the side button flips the display. Sadly, it does not remember which side you prefer. Another short press gets you onto AC volts, followed by ohms, followed by continuity and diode mode combined. Next is capacitance, and then temperature in Celsius, and finally temperature in Fahrenheit, and then back to auto. A short press on the side button gets you into AC amps mode using the current clamp. This meter has no DC amps. And a short press on the red button brings you back out to auto. By the way, there is no back key. If you wanted AC volts but accidentally clicked once too many and ended in ohms, you have to keep clicking your way through all the other functions until you get back to AC volts. A short press on live turns on live mode. According to the manual, a long press on live should turn on or off voice readout, but since this would be in Chinese only, they seem to have disabled this. Similar, the zero function is not implemented in the 268C model, but the torch function does work, although the light is rather dim and comes out at the bottom, which doesn't strike me as a very useful position for a torch light. Lastly, the hold button does the usual thing, and a long press allows you to dim the display should you so wish. I'm not going through all the functions, they all work as you would expect, just a few highlights. In auto mode, the meter is very quick in deciding the ohms and selecting the right range. This is quite impressive. I have seen much worse. In testing low ohms, it then actually switches to continuity. If you want to avoid this, you have to go into manual mode, press the red button until you hit ohms, and then test. Of course, at low ohms, you now have the lead resistance, which happens to be about 0.1 ohm, but as I said, 0 is not implemented, so you have to remember to subtract the value manually. Again, the auto ranging speed is quite impressive. In manual DC volts mode, it did not register the 1 mV input, but from 2 millivolts onwards it follows quite accurately single millivolt changes. I have absolutely no complaints here. This is good. Higher millivolt voltages are also fine. As with most smart meters, if you want to measure millivolts, you have to turn off auto. To demonstrate here, we have 10 millivolts input and the meter shows that no problem. Let me remove the probe and turn on auto and reconnect. Some strange ohm value appears and increasingly the input voltage just changed the ohms value. What happens is that the meter pumps out its own voltage in resistance mode, which interferes with the voltage coming from my calibrator, and it's interpreted as a resistance. This is not good for the meter and not good for the source, which in this case is my calibrator. When I reach 700 millivolts, something interesting happens. The meter goes back into the dashes of auto mode, meaning it can't decide what to do. Moving to 800 millivolts, and now the meter decides to use DC volts instead of ohms, and it shows the right value. A threshold of 600 to 700 millivolts under which they are blind for DC volts is common for smart meters in auto mode. This and the possible damage or at least weirdnesses caused in sensitive electronics by feeding voltages in resistance mode instead of measuring voltages is why it's best to get into the habit of not using auto when measuring voltages. As with most smart meters, it turns out that auto isn't all that useful anyway. Trying to measure a normal silicon diode junction in auto mode fails. But after switching manually to diode mode, it works just fine. Same with capacitance. You need to be manually in capacitance mode, but it does a reasonable job at small capacitances that many other meters don't even try. Okay, at the very low end, it's not accurate anymore. That should be 200 picofarad, not 99. On the high end, the largest capacitance I have handy is 2 parallel 4700 microfarad caps. Measuring large caps usually takes many seconds. At only about 5 seconds, the 268C is not bad. I already mentioned that continuity and diode mode is combined. That is unusual. Only older Fluke models do that too in my collection, but they always show volts. What is unusual in the 268C is that it automatically switches between showing ohms and volts. At more than 50 ohms, we're getting a display in volts. At 50 ohm, a single beep and a readout in ohms. And anything below 50, a continuous beep and readout in ohms. According to the manual, live should work by probing with a red probe. In my experience with other meters, you do not plug in the other probe for safety reasons. That obviously doesn't work in the 268C. If you plug both probes in, even though the black one is not connected, it does work, but now you have a probe dangling while you poke the other one into a main socket. I checked if there was anything on the black probe while testing with the red, and if I dim the lights, you can see that the lowest LED of the voltage testers are dimly lit. While that's not dangerous, it relies on the quality of the components in the 268C to remain safe. While we are at the subject of safety, this meter is charged via a USB-C port at the side. This is potentially very dangerous if the meter is used at the same time for measurements. At least they thought about this problem. Watch what happens when you plug in the USB lead into a charger, or in this case an extension plugged into a charger. With a click, the meter turns off and remains so until you unplug the charger. That makes it impossible to do measurements while charging, which is good. It still leaves the danger of keeping the USB lead dangling from the meter ready to be touched accidentally while doing measurements. So, let's test how well the USB port is isolated from the probes. I am measuring mains voltage at about 235 volts. The little breakout box allows me to conveniently probe the USB lead with a voltage tester against earth. And I'm happy to see no LEDs lighting up on touching either the USB plus or minus or the outside shell. I would still recommend never to keep the USB lead in and always use the bung to cover the port, just in case. Since the main purpose of the 268C is to measure leakage current, I decided to spend some time on that function. As a start, I measure the accuracy of the very low currents that we are dealing here, and I must say the 268C is surprisingly good at that. I'm using a signal generator for this, hence the current limiting resistor of 100 ohms. For higher currents I use a mains transformer. The results are in this chart, tracing the performance from 200 microamps to 10 amps against the BM869S, which of course has its own accuracy spec. The extremes at the low current end are caused by the limiting resolution of the 268C, where a single digit difference is having a huge effect on the error percentage. Overall, this looks pretty good, especially considering that this is a true RMS measurement and a bandwidth of 2 kHz. Power sockets are pretty tight for clamp meters, and I made myself such an adapter, which is actually just a mini extension cable. I am using UK sockets and plugs, but you can easily construct something like it for the standards used at your location. There's nothing special here. The three conductors live, which is the brown wire, neutral, which is blue, and earth, which is yellow-green, are connected straight from the plug to the socket. The only special thing is that I removed the outer insulation to expose the three cores, so they can be clamped individually. This removal needs to be done with some care to avoid nicking the insulation of the core wires, and for the same reason the whole rig needs to be treated gently to avoid damaging the wires. Understand that if you build and use something like this, you do it on your own risk. If you clamp all three conductors, which is the same as if you just clamp the cable without removing the outer insulation, you will normally measure just 0, regardless if there is current flowing to the load or not. This is because the current in the L wire is the same as the one returning in the N wire, but coming from the other side, the two magnetic fields cancel each other, and since there is no current in the E wire, a clamp meter around all three conductors will just show the total, which is 0. It is important to understand that in such a measurement, 0 doesn't mean no current is flowing. There could be hundreds of amps, but for the clamp meter they cancel each other. This incandescent bulb lights up, so clearly there is current flowing, but with all three conductors in the clamp, the result is 0. To measure the current drawn by a load, you normally clamp only a single wire, which can be either L or N. The meter will show the current drawn when the load is turned on. With just the brown live wire in the clamp, the meter shows the current of about 260 milliamps. Multiply this with 230 volts and you get 60 watts. No surprise, as this is indeed a 60 watt incandescent bulb. Leakage occurs, for example, when for some reason not all the current in the L wire is flowing back to the N wire. There could be some current flowing to the E wire, or there could be another path to earth that takes some part of the current. Most importantly, that path could be you, sticking a knife into a toaster to get some bread out. To save you from harm, most modern house installations have a thing known under many names like RCB, RCCB, RCBO or GFCI. This device compares the current on the L and N wires, and if it detects an imbalance, it breaks the circuit, thus saving you. They usually trigger within milliseconds when the imbalance exceeds 30 milliamps, and they usually have a test button causing a deliberate imbalance, allowing you to check that they still work. Apart from silly things like knives in toasters, there are other causes that could cause a little bit of leakage. If you have many devices plugged into the same circuit and each causes a little bit of leakage, then the leaks accumulate, and it's quite possible that eventually the 30 milliamp threshold is reached. These trips can appear quite randomly, and they are a real nuisance. This problem is more likely if a house has only 1 or 2 RCBs for everything, but even in more modern installations where each circuit has its own RCB, it's possible for accumulated leakage to cause a trip. This is where meters like the WinAPEX 268C comes in handy to find the culprits. Sometimes it's just a question of moving a device with high leakage to another circuit. So, for example, does this simple incandescent light bulb contribute any leakage? The answer is no, and there isn't really anything here that could, but you will find that a lot of things in the house have a bit of leakage, especially things with mains filters or surge protection. Here, for example, is an imbalance of 1 milliamp, but as there are several devices connected, I can make that larger by turning more things on. reaching 1.68 milliamps of accumulated leakage. The actual power consumption measuring just the L wire is now 0.7 amps, so all these devices together draw about 160 watts. What are they? A couple of multimeters, 2 function generators, a scope and a component tester. None of these are faulty, it's just the way they are built. I turned them all off again, and to my surprise the load current is not 0, but still 0.75 milliamps. That is less than 0.2 watts, but why? Then I saw that one of the power strips has a neon indicator, which of course is still on. While that explains that there is still power consumed, I'm wondering why there is a current of 0.15 milliamps on the earth wire. I would assume that the neon bulb is between live and neutral only. Interestingly, there is no imbalance between L and N, so if L was 0.75 milliamps, N is also 0.75 milliamps, and this balance is confirmed if I measure all 3 conductors, which is again 0.15 milliamps, the same as the current in just the E wire. I can only assume that both L and N leak equal amounts to E. One has to remember that most power switches on devices are not double pole, so even if they are turned off, some part of their main circuitry, possibly including a filter, is still connected. Here's another interesting case. A simple 20-meter extension lead. Let's plug it into the rig and power it on. With a clamp on L and N, there's an imbalance of already 0.08 milliamps, and there is nothing connected to this extension cable. The current on L is 0.17 milliamps. The blue N wire has only 0.08, and the earth wire carries the rest, also 0.08 milliamps. Measuring all 3 conductors together reads 0 because the current in L is compensated by the currents in N and E. And of course, you get the same by putting the cable itself into the clamp. Measuring the resistance between L and N, and as you expect, it's higher than what the resistance mode can measure. But for such cases, some meters, including this one, have a conductance mode. Letting it settle for a while, it shows a conductance of 0.55 nanosiemens. To convert nanosiemens into ohms, you need to take the reciprocal, so 1 over 0.55, and nano means 10 to the power of minus 9. The result is 1.8 gigaohms. Clearly this is not the cause of the leak. But here we are using AC, not DC. Let's see what capacitance the cable has. Zeroing the residual capacitance first. We get 1.82 nanofarad. Now, to convert that into reactance, we need to take the reciprocal of 2 times pi times the frequency, 50 Hz in this case, times the capacitance. And it gives us about 1.75 megohm. And dividing the mains voltage of say 235 volts by this gives a current of 0.134 milliamps, which is reasonably close to the leakage current we measured earlier. Finally, let's have a look inside. A total of 5 screws hold the rear panel. I actually assumed that the outline of a battery compartment door was just a fake, basically a leftover from an earlier version, but I was wrong. This meter has a real battery compartment. Sorry, the whiting is hard to read, but the battery pack claims a capacity of 750 milliamp hours. There isn't much to say about the inside. The brains is an anonymous blob. Protection seems very basic. I suspect the relay at the bottom right is responsible for shutting down and probably disconnecting the probes during charging. To the left of the blob is the buzzer. I wonder if this is also used for the Chinese voice readout or if there would be a separate speaker, but I can't see a connection point for it. The meter draws about 54 milliamps, and with a 750 milliamp battery, that should be comfortably more than 10 hours of operation per charge. So far I'm still using the charge that was in the battery when shipped. The specs of the meter. It's 6000 counts and the accuracy specs are okay, but similar to many meters these days. The reason why you may want the 268C specifically is the sensitive AC amps mode. Of note, there are 3 different models of this clamp meter, which is why the 268C has buttons that don't seem to do anything. The 268B model has the most functions in that it can do both AC and DC amps, and with higher currents than 100 amps, and it also has frequency measurement. But only the 268C model has the sensitive 60 milliamps AC amps range needed for leakage tests. All in all, I'm quite impressed by this meter. I like the large and bright display, and I like using it to test all kinds of devices for unexpected revelations on leakage currents. I leave a link in the description of this video where you can get it. If you like my videos, don't forget to subscribe and maybe consider becoming a Patreon. That would really help this channel. The link's in the description. Thanks for watching.